go ahead and apply our understanding of atomic size to answer these questions. It should take 4 minutes. Go. You can talk to each other more than 5. Person to your right, to your left, in front of you, in back of you. So sharing the answers, then any you want to go back and discuss, we absolutely will. Now, number 1, that's a little tricky, especially because they are in different periods and groups. If this kind of a question came on Friday, I would have asked, given these choices, which is the smallest? I think that is definitely a clearer one to choose. So it's asking us for largest. So we want to choose the one that is furthest down a group and furthest to the left. Yeah. So I think of the choices, magnesium. Yeah. I think we could easily say smallest. Then we want to choose furthest to the right and furthest up. Silicon, I think, is a clear, like, yeah, that feels more comfortable. All right, number 2, C. Number 3, A. Number 4, A. Number 5, C. Number 6, A. Number 7, D. Questions for me? Okay, so if we go to the very next page, now at this point, we should just know what cation means and know what anion means. All right, Nick J, could you choose an element for us that you know forms a cation? Perfect. So, size of neutral sodium versus the size of sodium +1, which is its common, of course, cation charge. So let's compare these, but then also, Adelaide, could you choose an element that you know forms an anion? Perfect. So what about the size of neutral oxygen versus the size? Now, oxygen will take a -2 total anion charge. So we'll go ahead and, but we could also say just oxygen with a -1, how that would change. Okay. The nuclei attracts electrons. Opposite charges attract, where same charge repels. There is electron repulsion. And that is a higher energy situation. That's a little distressing. So if an atom can do anything, they naturally do this to lower energy or to minimize repulsion, that's going to happen. That's what drives the size change. Okay. The size of a cation is always smaller than its neutral atom, but the size of an anion is greater than its neutral counterpart. And it is not because we're adding or removing electrons and they take up so much volume. That's not it at all. It's when you remove an electron, and form a cation. So the cation size is less than the neutral atom size because removal of electrons lessens electron repulsion, allowing the volume of the electron cloud to decrease, which equals a smaller radius. We don't repel each other. So imagine if we all, stood in a circle holding hands. Oh gosh, just imagine this, yeah. And we straightened our arms so we were still holding hands but far apart. And then imagine if Bennett gets called to the office because $100 check is waiting for him. Well, if Bennett leaves, we still want to be touching each other. And so we're going to have to come a little closer so that these two can then touch. But the deal is, if Bennett were an electron and he leaves, then, guys, we can get a little closer because we don't have to space each other out so much because we don't have as much repulsion. So that's why. But we can envision it like circle holding hands. So the opposite is true when we form an anion. So anion size is always greater than the neutral atom size because addition of electrons increases the electron repulsion. So that increases the energy situation. Ugh. So to minimize the energy, so as a result, the volume of the electron cloud increases to minimize energy, which equals a larger radius or atom size, ion size. Questions about comparing neutral atoms to each other and why the size changes as it does? If you were asked to choose between fluorine and fluoride, which is larger, all day long, fluoride. If you're asked magnesium plus 2, which is larger, all day long, the neutral. Cations smaller, anions larger. Okie dokie, moving ahead. Next page. So it's page 13 of this additional packet. Okay, ionization energy. Ionization energy is the energy required. So that means we have to put it in. The energy required to remove an electron from an atom or ion. To remove it out of the atom. So we're not just exciting the electrons and letting them relax and maybe give us some visible light. We are removing it. So if we take, Max, could you choose any element, sir? Sounds good. So if we take titanium and embed enough energy, and I'm just going to go ahead and call that ionization energy, like we know the value it needs to be. let's say we do. If we eject an electron, if we kick it out, well, then we form, let's see, Sabrina. If we take neutral titanium and remove an electron, what happens? What do we form? If we remove an electron. Very good. So we're removing negative, we become positive. If we are removing the first electron, it is first ionization energy. So if we're removing the first electron from the neutral atom, we call it first ionization energy. Are you able, Sophia, to get a picture of someone's rest of the notes? Perfect. Perfect. Very good. Thank you. Enjoy the rest of your day. But you can keep removing consecutive, and it would be the second one after you've removed the first. So we can keep removing, and then we would form the positive two and so on. Okay, in the table, and also this graph illustrates it, but I think it's nice to look at numbers. Lithium, beryllium, boron. Lithium, beryllium, boron. So lithium, and then we have beryllium and boron. That's where they are. Do you see how ionization energy is changing? Okay. Our atoms get smaller across the period. So we're getting smaller and smaller. The closer an electron is to the nucleus, the more strongly it's held, the greater the energy we have to invest to eject it. So when we go from left to right, ionization energy increases. Katie, as we go down a group, our atoms get bigger. So to remove an electron, will it require a greater or lesser investment of energy? Very good. Oh, decreases, yes. All right. If we had to evacuate for any reason, I don't know, a pipe burst, we had to evacuate. I know that, let's see, Nick, we're on the same wavelength. You are going to be holding your calculator to your heart because no one's going to get it from you. We have to evacuate. You're going to take the most precious thing that you have. Now, somebody else might like, oh, okay, my calculator, whatever. So what is easier to snatch it from? The closer it is or the further? Well, we know the answer to that. So the closer, that's the smaller the atom. Holding it nice and far, those are easy to pick off. Yeah? All right. Max, I'm sorry that I keep, but let's see. Bennett, Max, Ben, tallest. Or Cameron, tallest. Please don't, I hope no one's offended that I didn't put anyone else's name in that out there for tallest. What do you think? Who would we say is the tallest? Max, do you mind getting out of your seat? Okay, I appreciate it. All right. Okay, sir, we are going to play a game. No, just pretend. Pretend. All right, do you mind standing here? All right. You know what we're going to play? Tug of war. All right. So, tug of war. I put that on the 50 centimeter mark. Okay. And when Adelaide says go, we're gonna pull. Now, if we say like, okay, there. All right, and then when you get this there, then you win. If I get mine over here, that over here, I win. Now, if we legit do this, oh my gosh, faster than a blink of an eye, I'm gonna be on the floor, cleaning the floor as you drag me pathetically toward that side, with no effort on your part. We all know this. Yeah, no question, no question, no question. Okay. Atomic size, ionization energy. We're looking at the atom and judging how big is it, how much energy do we have to invest to kick out an electron. But electronegativity is one atom in comparison to another that are sharing electrons, sharing. And if they are sharing electrons, they are chemically bonded. In fact, what kind of bond involves shared electrons? Covalent. Yep. So we're going to covalently bond. And isn't that so nice, sir? Because we're sharing. Thank you. Because we're going to learn very shortly. Ionic, not so nice. Metallic. It's kind of like, covalent, Mr. Rogers. We're sharing. But guess what? It is not equal. It is a tug of war. Because I want the electrons. No. Okay, thank you. Yes.
To be fair, aren't ionic bonds nice in the fact that if you pair the right elements bond the right ones together, they both can become like fully stable.
You're right. But
So like they're the ones that want to lose an electron.
that is very true, but I still think like sharing so much nicer. We think, but actually not.
Well, that's compared to hydrogens together, it becomes that.
Very true. Very true. Very true. All right. Now, you are a big atom. What atom are you going to be? Oh, good one. I'm going to be chlorine. All right, sir. Now, chlorine, francium. Can you make sure that you don't let go of the meter stick, but don't pull so strong? Okay. We're not playing right now. We're just setting up the play. No, don't move your feet. Okay. If we could imagine, ladies, you can thank me later, Max's belly. His belly button is his nucleus. Now, bros, I will pay you guys. We're not going to talk about my belly button. Talk about my waist. See, Jillian's all in. See? Didn't know. Okay. My nucleus, your nucleus. You got 87 protons. I only have 17. But those shared electrons, guess what? They're way closer to me. So if we're going to play tug of war, who's going to win? Probably me. In fact, you probably are like holding on with your like bare, like tippy fingers. So who is going to win? So I wanted a much larger, more handsome, buff student compared to what we need to illustrate. We think in a tug of war, the larger will win. But it's all about, okay, how many protons are there and how close are the electrons to that nucleus? You guys know if you're playing legit tug of war, legit, don't you get down and you hold both hands and you're like trying to get close to your core, you don't kind of don't take it seriously. Not that you aren't, but you're not able to because the electrons that are being shared are so far from your nucleus. Max, if I said, would you mind helping me? We're going to play a game. If you said, no, thank you, I would have been totally fine with that. I respect that. Especially because you would have been acting like a noble gas. So if I asked you to play the role of argon and said, okay, we're gonna play tug of war, you would not have grabbed the meter stick. They already have their valence shell satisfied. They don't need to play, they're already good. There's one element that is the most electronegative. Who would take francium down? Which element is the strongest at playing tug of war for electrons? Remember? Because if we're asked to rank elements in strength of electronegativity, the closer an element is to this element, the higher its electronegativity. Ben?
Is it like oxygen?
Close. Close. I really appreciate it. Thank you. And thank you for not dragging me. I appreciate that. Okay. Electronegativity is on the very next page. And that is the measure of the pull an element has. It's really its nucleus, yeah? For electrons in a covalent bond. So they're being shared. Okay, the noble gases have a big old value of 0. Okay, so you just have to remember that. Okay, so I'm going to put a division line between the halogens and the noble gases. As one proceeds to the right, our atoms are getting smaller and smaller and smaller and smaller. So their electrons are pulling for are closer and closer and closer to their nuclei. So as we move across a period, electronegativity increases until the noble gases, and then it's nothing. As we move downward, electronegativity decreases because you're getting further and further and further and further. So no doubt that Mac's super strong, super nuclear strength, but the electrons he's pulling are just so far away. Me, just okay nuclear strength, but the electrons are much closer. So the element with the highest is fluorine. So you were close with oxygen. Fluorine has the greatest electronegativity. It is assigned a value of 4. And all the other elements are assigned values in comparison to fluorine. So fluorine is assigned a value of 4. Noble gases have 0. Hydrogen is, you don't have to know these, 2.1. You don't even have to know that fluorine is 4.0. It's just, I think if we know that fluorine is the most, then oxygen, chlorine, then nitrogen, and so on. Okay. Affinity. If you have an affinity for something, you love it or you really like it. So Nick has an affinity for his calculator, and I mean that as such a compliment. So electron affinity, we can think about likes, I guess, is the energy released when an electron is added to an atom or ion. Is added. So we could take sodium. If we add an electron, we are forming an anion. We are adding an electron closer to the nucleus than it was. So it's lower in energy. That energy is going to be released. If we want to think about purchasing tickets to a concert, you know, the closer you are to center stage, the more pricey the tickets, or center ice, or I don't know, behind home plate or whatever. The closer you are to the action. So the closer an electron is to the nucleus, the lower in energy, that's a greater cost. So just like a ticket, you know, to see, I don't know, Taylor Swift, could cost a lot of money the closer you are to the stage versus peanut heaven. So as we go down, our atoms get bigger and bigger and bigger. So these are the peanut heaven seats. So electron affinity decreases down a group, but it increases across a period. Okay, incredible students. So if we go back to our unit packet, could I please ask us on page 30, could you just answer the questions here? Not bad at all. Maybe 3 minutes, maybe. Okay, tomorrow we will just practice. We've done all of the teaching. Sorry that last couple trends were so quick. As long as we have size and we took our time with that, that's the most important. Enjoy the rest of your day. Yes, please. It's not terribly, again, maybe 4 minutes. Truly, yeah, all of it, please. Yep, we're good to go. Thank you very much for your participation.